Today we will be talking about appearance theory, and we are recording this just to remind everyone. We have our presenter Noah Morgan from our applications team, and if you're not familiar with our office hours format, Noah will do a presentation for about 20-25 minutes, and then we'll open it up to discussion of questions on his topic that he presented, or if there's something else in your mind that you need to ask about. Just put your questions in the chat box, and we will go over them when Noah is done presenting. As mentioned, we are recording, and you will get a copy of the recording right after the webinar concludes. And with that, I will turn it over to Noah, and we'll get started. Thank you.
All right. Thank you, Sherry, for the nice introduction. So today, Sherry said we'll be going over appearance theory, specifically the WaveScan, how it measures, what it measures, and we're also going to go over some scales that the WaveScan uses and what they mean. So to get started, what is appearance and what influences appearance? So appearance is influenced by several different factors, one being orange peel, which is essentially when the surface has the appearance of the surface of an orange. It's pretty self-explanatory, and we can see that in that top example, that right example specifically where it appears very wavy. And the second factor is called DOI, also known as distinctness of image. Some people call it brilliance as well. And this is when the reflected image appears sharper and clearer, or in other words, if you saw your reflection on a brilliant surface, you would see a near perfect reflection of yourself. So it's just a sharper image that it displays. So how do our eyes perceive waviness, specifically orange peel? In the example on the right, we see that the orange peel effect, or the waviness, this effect is seen on usually high gloss surfaces as a wavy pattern of highlighted and non-highlighted areas. So how does that happen? For example, if we have a light source like the sun and it's cast over a surface, or the surface will then reflect the light towards our eyes. But depending on the slope of the structure element that the light's being reflected on, that light will then reflect in different directions. So we can see in this example, the surface is wavy. So as that light hits it, it's not all going back directly towards our eye, but some of it's being scattered in different directions. This is where we'll see different perceptions of light and dark areas. You kind of think of it like a shadow effect caused from structures on a surface. So that's essentially our visual perception of orange peel. So this is another thing that we have to understand, which is the distance, our viewing distance, and how that affects what we're seeing. So in this case, we see that at 40 centimeters, we see shortwave. This is usually smaller structures. And then from 3 meters, we see longer waves. This is important because when we zoom out and we look at samples or objects from these further distances, we can't see shortwave anymore. The same is true as if we're looking for long wave at closer distances. We can't see the long wave. So these are just visual effects that are something to be aware of when looking for these appearances. This is a great example for this type of relationship. So think of this like the short wave and long wave relationship. If we're looking at a sample from a close distance, we can see some information. In this case, it's a pattern of letters. But as we move away from the sample and the distance increases, we can no longer read those letters anymore. But we can start to see that those letters are forming a pattern that can't be seen from close up. So the same is true with short wave and long wave. At close distances, short waves can be seen, while at greater distances, only the longer waves can be perceived. All right, so what exactly are these short waves and long waves that we observe from these different distances? So in the graph, we see that the resolution of our eye ranges from structure size that's around 0.1 millimeters and then greater than 100 millimeters. So from far distances, or 3 meters, we can best see the structure size of approximately 10 to 20 millimeters. That's referred to as long wave. And then structures smaller than 0.1 millimeter, we can't really see from larger distances. So then we move to our closer distance, which is around 40 centimeters, and we best see structure size of approximately 1 to 3 millimeters. So that's our shorter wave. We can't resolve structures that are below 0.1 millimeters very well because that's the limit of our human eye. But with those very fine structures and textures, those are what directly relates to the DOI. So they can affect the brilliance or the sharpness of an image, of a reflected image on the surface. So it's also very important. And that measurements below that of what we can perceive are referred to as dullness. So it's a different type of scale. So now we have a background on visual perception. We can move on to how the WaveScan actually measures these visual effects. So to start, the WaveScan is meant to be rolled across the surface and gather surface data using a laser point, a laser light source that illuminates a sample at a 60-degree angle. And then with a detector that's opposite of the laser at 60 degrees, the instrument will scan the surface and measure the reflected light intensity point by point. And then with all that information, we can create an optical profile of the surface. So here's a nice example of what that looks like. So as we roll the WaveScan across the surface, we can see that the structure of that surface will change the light intensity. So in this picture here, we see that the light intensity is very little because not all the light's going back to that detector and that sensor. Then we see as we roll across the surface, our optical profile changes, and a little more light gets reflected back towards that sensor. Then we see that it starts to focus in as it hits that other angle on that surface. And then finally, as we get into the valley of this structure here, we see that there's a very direct light intensity that's going right to that detector. So with all that information is essentially how the WaveScan will measure those types of surfaces and create that optical profile. So once we have that optical profile, we put that data through mathematical filters, and that's how we get the short wave and long wave. It's essentially just broken up into different scales. The short wave and long wave are referred to as the classical ranges, so the classical scales, because they're no longer looked at in a lot of industry, and that's because there are some shortcomings with these types of scales. And as we developed better and better technology with coatings and instruments, we needed better ways to look at that data. So we needed to separate the short wave and the long wave into different scales. But as good background information, the short wave classical range is around 0.3 to 1.2 millimeters, while the long wave is from 1.2 to 12 millimeters. So here we can see how the short wave and long wave data correlates to our visual perception. So in sample A, we see that the short wave and long wave values are fairly low, and this gives us a relatively smooth appearance. Whereas sample B, we see that the short wave value is higher, slightly higher, and the long wave value is a lot higher. Then when you look at the sample, it looks a lot wavier than sample A, and it's very unpleasant to the eye. So here are two more samples, but these samples kind of highlight the issues with using just the shortwave and long wave system. So sample C appears visually wavier. We see that it has a lot higher shortwave and a very low long wave. And then we see sample D, which appears to have more smaller structure. It looks rough, but we see that the shortwave and longwave for this sample are exactly the same. So in these examples, we can see that now there's a need to further define structure sizes and get a better understanding of what's actually happening on the surface, because just two scales isn't enough data to really understand the full story of what's happening to make it appear the way it does to us. So this is where new scales came into play. We can see that those mathematical filters used on the optical profile once again, but instead of just breaking into the shortwave and longwave, we see that it's broken into different structures, specifically different structure sizes and scales. So we have an increased measurement range of 0.1 to 30 millimeters, higher resolution from 0.1 to 0.3 millimeters. The long-wave range gets divided into two ranges to obtain more detailed information. So we see that highlighted in the red. The shortwave gets placed into a separate scale there, what's highlighted in the blue. And this is a detailed slide here that shows the separation and specifically the types of structure sizes that each of these new scales use. So we see that the shortwave, which is that blue region there, is now the WB scale, and the long wave is broken up between the WC and WD. And we have new ranges for each of these scales. Our WA is from 0.1 to 0.3 millimeters, so very fine structure. Our WB is 0.3 to 1 millimeter, and our WC is 1 to 3 millimeters. Our WD is 3 to 10 millimeters, and our WE is 10 to 30 millimeters. So it looks at a larger and more data, so we can see really exactly what's happening on these surfaces rather than just these two scales. So now with the additional scales, we can see the full picture. So using the structure spectrum graph, we can see that sample C has a lower WC value, which gives the impression of a better balance of small and large structures, whereas sample D has a high WC value, which shows us that it has high amounts of structure across the scales, which gives us an exaggerated orange peel look. And we can see that there. Because the additional scales can show us more of what's happening on the surface, we can then predict what a better overall appearance will look like using measured values and structure spectrum curves. So, back there. So what about structures that are too small for our eyes to detect? So this is where, referred to earlier, I mentioned dullness, and this is where dullness comes into play. So these are structures that are so small that our eyes can't perceive it. And this is what distinctness of image, or DOI, is. So we see on the example on the left, the reflected image on that surface is very clear and very sharp. We can make out exactly what it is, whereas the example on the right is a little dull, it's a little blurry, it's not as sharp. And so these are important qualities. You want to have a very nice appearance on your end product. We need to be able to measure, what's happening on these smaller structures. So this is an example of how DOI is influenced. So we have some microstructures, which are smaller than 0.1 millimeters, and they cause a diffuse scattering of light, which then leads to a contrast reduction. Then we have structures between 0.1 and 1 millimeters that cause distortion on the edges. So this is where outlines become blurry and are no longer sharp. And it's also important to remember that, like I said before, these are structure sizes that are at the edge of our eye's ability to see. So it's important to be able to use this instrument to measure that effect accurately. And so this is how the dullness measurement comes into play. And this is how it's measured on the instrument itself. So basically what happens is a green LED light illuminates the surface at 20 degrees, and then a camera detector analyzes the reflected image of the light source. And if there are no fine microtextures, all the light will be reflected and detected in the middle of the camera. So we see that there, it's almost like a target. If there are fine microtextures, then you'll have scattering, and some or all of the light will be scattered on the outside of that detector. And that is also picked up. And then that ratio between what's scattered and what hits the middle of that sensor is put into a calculation, and then that's how we get our dullness value. So what are the advantages of the dullness measurement? Well, the dullness is independent of refractive index because it's not an absolute measurement, but more of a relative measurement. Unlike gloss, which is entirely dependent on refractive indexes, an example of this would be if you were to measure a 2K clear coat and a 1K clear coat, the surface would visually look the same, and a glossimeter will give you two very different readings, but your dullness values will be exactly the same. The reason for that is because the gloss is dependent on that refractive index. We can see in the image there, our 2K clear coat is around a 1.5 refractive index, whereas our 1K is around a 1.53 to 54. So this can change how that light is interacting with that surface. Therefore, your gloss meter will give you different values because of the densities, and the dullness value that's measured on the WaveScan will give you the exact same measurement because it's looking at that reflected image. Other advantages is that you can measure the dullness on a curved surface. So typically gloss is not recommended for curved surfaces because you have this light scattering effect that doesn't make it back to the sensor. So it's not giving you a true value of what that gloss actually is. But in this case, the WaveScan is able to measure dullness over those curved surfaces. So by adding the dullness value, we then get the complete structure spectrum that the WaveScan measures. So we can measure structure size from less than 0.1 millimeters, which is our dullness, all the way up to 30 millimeters. So this encompasses the dullness, the WA, the WB, WC, WD, and WE scales. The scales go from 0 to 100, where the lower the number, the better. What's important, though, is the ratio between the short waves and the long waves, because you really want a balance of the two types or the scales there. So you want to have a higher or a slightly higher short wave structure than your long wave structure. Sometimes people say a 2-to-1 ratio, but that's not entirely true. It really depends on that full structure spectrum. And then here we see the DOI calculation at the bottom. We can see that essentially includes all of the shorter wavelengths and smaller structures because those are what affects that visual DOI appearance. We see that it's a function of DU, WA, and then WB. So now that we know how and what our WaveScan measures, what are the applications and uses? First, we can use it for quality control for raw materials like substrates. You can use an R&D for measuring paint materials and how they affect the end appearance. And of course, you can use it to collect data that can then be used to detect errors or issues along the painting process of products. So it has a lot of different uses. What we'll look into is the use of it detecting issues along a process because it's a very key aspect that the WaveScan can do. So we see here some examples of the structure spectrums and what the surfaces actually look like. So we see at the top example, we can say that's our original. It has a very not pleasing appearance. It's pretty rough and orange peel-like, very wavy too. And we see that our structure spectrum reflects this look. So we see that the short and long waves are pretty high across the board. The WC is very high as well. And it's not that 2-to-1-ish ratio that we'd really like to see. So what we need to do is we need to lower the long waves so that we can get a better balance between those short and long wave structures. So how do we do this? In this case, the first step would be to optimize the clear coat application by increasing the clear coat thickness, which will then lower the WC and WD scales. So we see that on that bottom example. So we see that there's less orange peel. So it looks better, but it's still a little rough. It looks a little sandy almost. We can see on the right side, how that structure spectrum curve changes after optimizing that clear coat. So we bring those long waves down very low. So after we did the optimization of the clear coat, we want to make that look better than what it is now. We still want to improve it. So what we could do now is we can sand the primer. So we need to remember that all parts of the process contribute to the end appearance. So this includes everything from the substrate to the clear coat. And then after sanding that primer, we now see that the short waves have drastically decreased and the long wave becomes more dominant. The orange peel effects becomes apparent again. So we see in that scale, or that structure spectrum, how that changes now with that red line. We see the short wave drastically decreases. So how do we optimize it once again? We can optimize the top coat and the clear coat application. So then this creates a balanced appearance between the short waves and the long waves again. What we're really looking for is the smaller structures to be slightly higher than the larger structures on the spectrum, like I spoke of before, because that's the key balance that we're looking for. It gives the best visual appearance in the end. So we see after we optimize that primer and top coat, we see it creates more of a wet look that's more desirable than the other previous examples. And usually if you go outside and look at any car, this is typically what you'll find across those vehicles, is that type of surface in that bottom sample. So then again, this is all the samples that we just saw previously, but shown all together so you can see how the sample visually changes after each process. The visual perception changes dramatically depending on which area of the structure spectrum changes were done. So to recap, when we started, both short and long waves were high. So we optimized the clear coat to lower the WD and WE scale in their values. Then we had higher short waves, so the WA, WB, and WC were higher. So we sanded the primer to lower those values. And then we saw that we lowered the short waves too much and needed to increase the short waves to balance the spectrum. So we optimized the primer and the top coat. And that gave us our final image at the bottom there. So we can see how, we can use the WaveScan values to really figure out what we need to do in order to fix something along the process or improve the visual look so that the end appearance is the best that it can be. And that concludes this short presentation. So now we'll leave it open for questions.
Thank you, Noah, very much for that overview and information on orange peel and the WaveScan and long wave and the short wave. And we do have a couple questions. How do you take those pictures of the samples to compare the visual waviness in the DOI to the WaveScan measurements?
So these, I believe you're referring to this. I'm not sure how they did it, but what I would assume is that they took these actual panels and they took the measurements of it with the WaveScan, and that's how they were able to make that structure spectrum curve. And then they were able to take pictures of it, and then they would change different things about the process, and then they would take a picture of that next sample to see how it changed. Does that answer your question?
Robert, just wondering if that did answer your question.
Oh, this is Ray. I can add a little bit more to it. So basically what they do is they take a picture. They have like lights that are running across a panel on the ceiling. They put the panel underneath, and that's how they take the picture. So there's a light in a dark location like you can see on the panels. And then like Noah said, we just measured that same panel to generate our curve. So that's how they do it.
Thank you. And then just Noah, why again are there two scales for the long wave? Was that just to gain more clarity in those two areas?
Yes, so I'll go back to the slide here. So we separated the long wave into the WC and WD, and this was to increase, the data that we could collect. So instead of just collecting just one value for the range of 1 to 10, 1 to 12 essentially, we're now separating it into two so we can get more detailed information out of that range of structure.
Thank you.
So for the WD, a lot of things that affect WC in that wavelength area are different than what affects WD. So when you leave long wave grouped together in that big range, it's harder for you to figure out what's going on in your process and make changes to improve your visual analysis and the numeric analysis of the coding.
And then I think you mentioned that, dullness is its own value, and we see that as the DU value. Is that correct?
Yep, so that's correct. Let me bring up that slide here. So our dullness value is what we can't see with our eyes. It's usually very fine structure, but what that very fine structure does is it scatters the light so that those fine structures are what defines a brilliant, very sharp reflected image or a very dull, non-clear reflected image. So it's an important thing for DOI measurement specifically because it's part of the calculation for DOI and distinctness of image. But we can't see it with our eyes. And it's almost like a separate measurement or a separate scale that's able to determine what that DOI will look like.
If there's any other questions, please feel free to put them in the chat. Oh, we do have, yes. What are other supplementary analysis that should be used when assessing surface appearance? Is WaveScan alone sufficient?
So that's a good question. It depends on what you're really trying to look for. It also depends on what you're measuring. Usually if color is involved, you want, a color measurement device, or, if it's an effect pigment that you're using, you want a multi-angle color measurement device. If you're measuring surface profile of detailed structures, you can use a profilometer, which measures the surface profile and usually these different types of microtextures. But at that point, it doesn't relate to waves anymore. It's more of detailing different structures, almost like if you were to measure a basketball. It usually has these very small dots on it. So that's what you would use a profilometer for.
Robert, if you need us to contact you, we can discuss it further if needed, or I can unmute you at this time if that helps. If you have an additional question on that. We have another question. Is there an ISO standard that describes this test method?
I'm assuming you're referring to the WaveScan and its measurements. Let me check here. I don't believe there is an ISO standard offhand. I can certainly check in 1 second.
While Noah's checking, a lot of times the customers specify what equation that they want used for their pass-fail. So it's more based on like what customers are requesting you to show them for data. And then if you don't have a customer specific spec, we recommend that you use the whole structure spectrum, because that really helps you change your process to improve your appearance or change your material to improve the appearance.
Yeah, so piggybacking off of what Ray said, there's no standard essentially for measuring this type of appearance with the WaveScan. But what you're really looking for is how you want your finished product to look, and then creating pass-fail tolerances using equations that'll take into account the structure spectrum with all those different scales from the dullness to the WE, in order to make your process more likely to have that end result every time. So you can measure that against different samples to make sure that your quality control is always getting the best result.
So what I'm hearing you say is that you want it to you want a standard to match whatever you're trying to achieve, not that there's necessarily a universal standard out there you're trying to meet. Because
exactly.
I always confuse it, but isn't it more of like, for example, the high-end cars tend to have a more or less orange peel versus the lower end, just because it gives it more of a brilliant look. And like I said, I might have that backwards, but yeah.
Yeah, you're absolutely right. A premium car, say like a McLaren, usually what you'll see is they'll use a lot more clear coat, which will diminish the amount of surface structure, so you won't see as much surface structure in it, and the brilliance will be very high, so you'll be able to see your reflected image perfectly almost, rather than the like regular lower end cars that you would buy. If you really go outside under the sun and you look at different angles, you'll see that it'll have some type of waviness in it.
We do have another comment that there are two ASTMs, gloss D523 for specular and D5767 for DOI. So I don't know if you have any comments on that. Yes.
So those are just the ASTM methods, how you calculate or how you measure gloss, and then how you calculate DOI. They're not for the whole entire instrument and everything that it does. So those are just two. The gloss doesn't even get measured with the WaveScan meter. It gets measured with a gloss meter, but DOI can come from here. But other people have DOI instruments that only measure DOI, and it uses this specification, and ours also does.
Another question we have is, so is dullness part of the BIC WaveScan equipment, or is it a new thing, i.e. less than 0.1 micrometers?
Yes, so it's part of the WaveScan equipment. but it's not really a new thing. Ray, do you have anything to add to that?
So it depends. If you're using like a Toyota meter, then they do not calculate dullness on that. But this has been ever since we came out, 2000-ish, I think. With the new WaveScans, we've always included dullness because it's very important, especially if you have really fine structures coming from like a substrate or something like that. Without the dullness calculation, you can't, or without the dullness, you can't really quantify that whole structure for the whole entire coating. So you're missing a portion if you don't have dullness, because it gives you that fuzzy appearance that sometimes is hard to explain to people. It gives you a number that correlates to what you see visually.
Are there any other questions at this time?
And just a comment from me again, it's really important. I know a lot of people have a specification that's required by their customer to meet, or even within their own company to meet. But if you're trying to improve your appearance, you need to look at the whole structure curve. And we can always help you if you have data and say you're not sure exactly what to try. It's not an exact science. We do have to, sometimes turn a couple knobs and see how that affects your structure spectrum curve. And then we can figure out how to fine tune it better to get your appearance better on your parts. So it's really important, in my opinion.
And while we're waiting to see if there's any other questions coming in, I would like to mention that later this month, we do have a dispersion webinar on the 19th and visual color evaluation of solid colors on the 21st. When you received your last invitation, you should have been able to see any of the webinars and office hours that we have coming up, and you can feel free to sign up for as many of those as you like that apply to you. And you can always reply to any of those messages as well if you have any questions, and I'll be sure to get you to the proper person to answer your questions. Noah, did you want to add anything else today?
Yeah, I can add. If you're unsure if you should get this instrument, or if you have any concerns with how your material will be measured with this equipment, we do offer a service where you can send in samples to me, and I can take some measurements with our instruments and see how the data looks when measured on your material. And then we can have a meeting and discuss, why it's looking like that, or, discuss the values that are behind, that are measured with your sample, and really see how it can affect your process to have this equipment, and what benefits it'll bring. And if you have any, if that's something you'd like to do, you can always reach out to me. I put my email up on the screen again, and we can arrange samples to be sent, and we can go from there.
Oh, someone is typing, so wait just a minute. Oh, thank you. You're very welcome. Thank you. And since I don't see any other questions coming in, we can give you back a little bit of time in your day. I'd like to thank everybody for taking some time to join us and attend our office hours. I'm hoping that you learned something new, or had a little bit more clarification on something. As mentioned, you should get the recording of this, and then you can review it or share it with anybody that wasn't able to attend. And we look forward to seeing you in some of our future webinars. Thank you.